So the next two topics that you're going to learn are empirical and molecular formulas. So in the beginning, you learned that there are two ways to represent a compound. The first one is via molecular models, and the second one is via chemical formulas. And there are three different types of chemical formulas. The first one is empirical, second one is molecular, and the third one is structural formula. And as I mentioned earlier, we're going to cover structural formula in a lot greater detail later on in this semester in chapters 9 and 10. And so in today's lecture, we're going to focus on the first two, which are empirical and molecular formulas. So just a quick recap on definitions here. Chemical formula basically represents compounds showing the elements that make them up and their numbers relative to one another. And there are three different types, but again, our focus here will be on empirical and molecular formula. So empirical formula, by definition, basically shows you the simplest whole number ratio of the atoms or moles of elements in a given compound, whereas molecular formula shows you the actual number of atoms or moles of elements in a given compound. And so I mentioned earlier that empirical formula is basically the simplified version of the molecular formula. So let's look at some examples here. Let's say benzene, C6H6. So this is a chemical formula, okay? And more specifically, molecular formula. So if I ask you, what is the empirical formula for this compound? Well, if the chemical formula can be simplified further, then what you get is the empirical formula. So you can see that the ratio between carbon and hydrogen in this chemical formula is 1:1. Right? So you have 6 carbons and 6 hydrogens. So if you were to divide both numbers by 6, which is the common denominator here, you get 1. And so you can simplify this by dividing the numbers by 6. And so you get C1H1, or simply CH. So CH, in this case, is the empirical formula for this compound. Let's look at the second one right here that we looked at earlier in the beginning of the chapter, H2O2, which is basically hydrogen peroxide. And it has the chemical formula H2O2. And so if you simplify this, you just divide both numbers by 2, the common denominator, and you get H1O1 or HO. And the third example here is C2H6. You can see that the common denominator here would be 2. And so if you divide both numbers by 2, you get C1H3, or simply CH3. And the fourth example that I have here is sugar or glucose. It's C6H12O6. And so you can see that you can simplify this further by dividing all numbers by 6. And so you get C1H2O, or simply CH2O. So that's the difference between molecular formula and empirical formula. So the idea behind this concept, known as empirical formula, is that it allows you to determine and calculate the compound's molecular formula. Let's say that you are able to synthesize a new medicine that can cure some disease, but you don't know its chemical formula. And so the first step is to determine what kind of elements are present in that compound. So you perform elemental analysis experiments. And let's pretend that you determine that that compound is composed of carbon and hydrogen. And according to your elemental analysis report, you get the total masses of carbons and hydrogens. And then from there, you can calculate the empirical formula from the data that you just obtained. And then ultimately, the molecular formula. So how do we determine the empirical formula of a compound from a given data? Well, empirical formula can be determined from experimental data, like, for example, elemental analysis. So normally you get the masses of the elements in grams or kilograms or other units of mass. Sometimes you can also get percent composition from a given data. But how do we extract that data and get the empirical formula? Let's look at some examples here. So let's say that you performed the experiment and you were able to obtain the masses of all the elements that are present in that compound. So let's make it simple, and we're looking at water, right? According to your data, water decomposed to 0.837 grams of hydrogen and 6.86 grams of oxygen. So we have the mass. So that's our data. Determine the empirical formula. So how do we do that? The first thing you want to do is to convert the masses to moles, because if you remember the definition of empirical formula, it's the simplest whole number ratio of atoms or moles, not masses in grams or kilograms. Okay, so you have to convert the mass into moles or number of atoms, but for now let's focus on moles. So we're gonna convert mass to moles, and then we're gonna take the ratio, because this is the simplest whole number ratio, by dividing the resulting numbers by the smallest number. And then if the ratio is not a whole number, multiply the ratio by a factor to get a whole number. So these are the 3 steps that you need to take in order to get the empirical formula. So the first step here is to convert the masses into moles. So you're going to use dimensional analysis, and you know that the atomic mass of hydrogen is 1.01 gram per mole, whereas for oxygen it is 16.00 grams per mole. All right, so we convert grams to mole of hydrogen, and same thing for oxygen. So that's the first step. Second step here is we take the ratio of the two by dividing the smaller number. So the smaller number here is 0.429 mole of oxygen. So we're going to divide both numbers by the smaller number. So 0.849 divided by 0.429 for hydrogen, and then for oxygen 0.429 divided by 0.429. So we get 1 for oxygen. For hydrogen it's 1.98. All right, and then it says over here, if the ratio is not a whole number, multiply the ratios by a factor to get a whole number. Since the number that we have for hydrogen is pretty much a whole number because it's close to the number 2, we don't have to multiply it by a factor. But if you get something like 1.25 or 1.5, then you would have to multiply it by a certain number to get the next whole number ratio, or next whole number. So in this case, we're just going to round it up to number 2. So for hydrogen, that would be about 2 moles, and for oxygen, 1 mole. So in that case, the empirical formula of water is H2O. Alright, so let's look at an example here. A compound decomposes into nitrogen and oxygen. Calculate the compound's empirical formula. So you're given the masses of the elements involved in that compound. So you have 24.5 grams of nitrogen and 70.0 grams of oxygen. And so in order to determine the empirical formula of this compound, you need to follow the 3 steps. So the first step here is to convert the mass to moles for each element. And so we're going to convert 24.5 grams of nitrogen and 70 grams of oxygen to number of moles. And so you can use dimensional analysis, or you can just divide 24.5 grams by the atomic mass of nitrogen and 70 grams by the atomic mass of oxygen. And here we get 1.75 moles of nitrogen and 4.38 moles of oxygen. So this brings us to the second step. And it tells you over here to take the ratio by dividing the numbers by the smaller number. So the smaller number here is 1.75 moles. So we're going to divide both numbers by 1.75, and that gives us 1.0 mole for nitrogen, and 2.50 mole for oxygen. And according to the third step here, if the ratio is not a whole number, then you have to multiply the ratios by a factor to get to the next whole number. So in that case, when you look at the moles of oxygen here, it's 2.5. So this is not a whole number. And so what we can do is to multiply this by 2, and we get 5, which is a whole number. And since we're multiplying this by 2, we have to do the same thing for nitrogen. So we're going to multiply both numbers by 2. So now we have 2 moles of nitrogen and 5 moles of oxygen. So now we can write the chemical formula or the empirical formula as N2O5. So the subscript 2 here basically represents the number that you calculated. 2 moles and then 5 here for 5 moles of oxygen. And whenever you're writing the chemical formula, you want to do that in alphabetical order. So N goes first before oxygen. So here's another way to calculate and determine empirical formula from a given compound. And we can do so from mass percent. So let's say that you performed elemental analysis and you get the mass percent for each element for that compound. An example here is aspirin. And let's say that you determine that it contains 60% carbon, 4.48% hydrogen, and 35.52% oxygen. How do you determine aspirin's empirical formula? So there's more than one way to do this, to calculate this. One way is to convert the percentages into decimals, and you can consider that the mass. Like for example, if you have 60% carbon, you can convert that into 0.60 grams. And then for 4.48% hydrogen, you can convert that into 0.0448 grams, and so on and so forth. Or you can use the second method, which I will show you here. So again, we have 60% carbon, roughly 5% hydrogen, and roughly 36% oxygen. So what you can do here is you can imagine that you have a 100 gram of sample of aspirin. And if you say that it consists of 60% carbon, that means that in a 100 gram sample, you have 60 grams of carbon, okay? 4.48 grams of hydrogen, and so on and so forth. So now you can use the same method that you just did in the previous example by using the 3 steps. So you convert the mass to moles and then take the ratio and then multiply by some factor to get the closest whole number. So the first step here again is to convert them into moles. Okay. And then you're going to analyze the numbers and see which one is the smallest number. So you can see that this is the smallest number here, 2.220. And so we're going to divide every single number here by 2.22. All right, so we're going to divide all these numbers and we get these ratios here, right? So this is a result of the division. And so you get 2.25 moles of carbon, 2 moles of hydrogen, and 1 mole of oxygen. So the last two here are whole numbers, but the first one is 2.25. So how do you get rid of that quarter, that 0.25? Well, you can multiply this by 4, and that gives you a whole number. Okay, because 4 times a quarter gives you a whole number. So because we're multiplying this by 4, we have to do the same thing for the other two. So now multiply this by 4. 2.25 times 4 gives you 9. 4 times 2 is 8. 4 times 1 is 4. So we have 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. So now you can write this as C9H8O4, right? Again, you're writing this in alphabetical order: carbon, hydrogen, and then oxygen. So once you've calculated and determined a compound's empirical formula, you can get the compound's molecular formula as well. So molecular formula is the whole number multiple of the empirical formula. And so how do we prove that? Again, so when you look at these molecular formulas here, you can determine the empirical formula by simplifying the molecular formula, right? So you can divide C6H6 by 6, and you get CH as the empirical formula. For hydrogen peroxide, it's HO. For C6H14, it's C3H7, because you're dividing the subscripts by 2 to simplify it. And then the last one, CH2O. So how is it that molecular formula is a whole number multiple of the empirical? So you can clearly see here that molecular formula is a 6 multiple of the empirical formula. All right, so its multiple is 6. And then for hydrogen peroxide, it's 2. For C3H7, it's 2. And then for glucose, it's 6. Right? So they're multiple of the empirical formula, because when you multiply its multiple by the subscripts of each element, you get the molecular formula. So 6 times 1 for carbon, you get C6. 6 times 2, you get H12. 6 times 1, you get O6. So that's what it means by a whole number multiple of the empirical formula. And it's also true when it comes to the total molar mass. So when you look at the total molar mass of the empirical formula and compare that with the total molar mass of the molecular formula, you can see that molecular formula is a whole number multiple of the empirical. So in this case, the multiple is 6. So when you multiply 13 times 6, you get 78, which is the molar mass of the molecular formula. And you can do the same thing for the rest here, and it remains true. All right, so in that case, we can create or formulate a formula for. So you can see that the empirical formula multiplied by its n multiple, you get the molecular formula. So an example here is benzene, right? CH, multiply this by 6 and you get C6H6, the molecular formula for benzene. And this is also true for the molecular, or for the molar mass of the compound. So if you multiply the empirical formula's molar mass by its n multiple, then you get the molecular formula's molar mass. Here's an example. If you multiply 6 by 13, which is the empirical formula of CH, then you get 78 grams per mole. Okay, so let's look at this one example here. The molar mass of butadiene is 86.09 grams per mole. Its empirical formula is C2H3O. What is the compound's molecular formula? So we're given the molar mass of the molecular formula here. Okay, so this is the molar mass of the compound butadiene based on its molecular formula. Now, we can calculate the molecular formula if we know the molar mass of the empirical formula. We are given the empirical formula here, so we can calculate the molar mass of the empirical formula. So there are two equations that we're going to need. The first one is shown here on the left. Right, so we have molecular formula is equivalent to the empirical formula times n, and n is the multiple. Right, so by definition, molecular formula is a whole number multiple of the empirical formula. So we can solve this if we know the value of n, but right now we don't. And so we can use this second equation here to determine the value of n. So we're given the molar mass of butadiene, the molecular formula, but we don't have the molar mass of the empirical formula. We can calculate it. So we have 2 carbons, 3 hydrogens, and 1 oxygen. So we know the atomic masses of each element. We can calculate the molar mass easily. So 86.09 grams per mole for the molecular formula's mass, and for the empirical formula, it's 43.05 grams per mole. So now we can use simple algebra to isolate N. So we can solve for N by dividing 86.09 by 43.05. And this gives us 2. Alright, so now that we know the value of N, we can plug this number into this equation. Okay, we can substitute this number for N. And we also know the empirical formula, so we can just plug and chug. Distribute the number 2. And we get C4H6O2. So this is the molecular formula of the compound given the molar mass of butadiene and the empirical formula.